Hello, everyone. This is Zhuohuang from Indiana University, and today I'm very excited to give a presentation on our recent work, which is on loss functions and recurrency training for GAN-based speech enhancement systems. And here's the outline for my presentation today. I'll first give an introduction of our paper, and I'll describe the proposed GAN systems with its loss functions. Then I'll talk about the experimental setup and the simulation results. Finally, I'll give the conclusions of our study. So basically, the goal of the speech enhancement is trying to remove the background noise and interfering sources while maintaining the target speech. So it was proposed to solve the cocktail party problem, where you have multiple talkers, background noises, which makes you difficult to hear other people's talking. So the applications of the speech enhancement system include, it could be used as front ends for the ASR systems, and it also could be implemented in the digital hearing aids to help people with hearing impairment. So prior studies on speech enhancement systems, basically there are like the time frequency mask-based approaches, but usually they transform the speech from time domain to time frequency domain spectrogram using the short time Fourier transform. So by using deep learning approaches, they can estimate a time frequency mask that can be used to apply on the noisy spectrogram to get a estimated enhanced spectrogram, then using the inverse short time Fourier transform to reconstruct the time domain enhanced speech. So that's how the TF domain mask-based approaches works. There are also different types of networks that has been investigated, including conventional DNN-based approaches with the ideal ratio mask, complex ideal ratio mask estimation. There are also like recurrent neural network approaches with the ideal ratio mask, phase-sensitive mask estimation, and people notice that a better performance can be achieved by the RNNs, since the recurrent structure can better capture the temporal information inside the speech signal. So in terms of the GAN-based network for speech enhancement systems, so it has only been investigated in recent years. So a typical training scheme for GANs including 3 steps. So in the first step, we train the discriminator given the clean speech and making the target as real to update the weights in the discriminator. And in the second step, we're going to use the information from the generator, but at this time we freeze the weights in the generator, and we only update the weights in the discriminator by forcing the target to be fake. Then in the next step, we freeze the weight in the discriminator, and we only update the weight in the generator, and forcing the target to be real. Then we just do this, keep doing these steps one by one to train the adversarial networks. And the motivations for this work are quite straightforward. First, we noticed that the current GAN-based speech enhancement system, they often adopt different loss functions while using different network structures. So it is not clear what is the best performing loss functions for training such a system. It is also not clear whether the adversarial training scheme would actually be helpful, because those systems have not been compared with any other non-GAN-based approaches. And it is also not clear if including additional recurrent structures with the convolutional architecture would be beneficial. So here in our study, we propose a convolutional recurrent GAN denoted as CR GAN for speech enhancement. And we also investigated different loss functions for our CR GAN model. And the influence of recurrent structure on the objective performance is also investigated. We further investigate the influence of introducing an adversarial training scheme by comparing our CR GAN with a with a convolutional recurrent network that is without the adversarial training scheme. We further compare the system performance with other non-GAN-based speech enhancements systems. So here is a general network architecture for our proposed CR GAN system. As I mentioned earlier, it consists of 2 parts, a generator and a discriminator. So inside a generator is basically a variant of the convolutional recurrent network, where it consists of an encoder, a decoder, and in the middle layers there is a recurrent network, consists of 2 layers of bidirectional LSTM to capture the long-term temporal dependent information. So inside the encoder, there are 5 layers of 2D convolutional layers with spatial normalization enabled, and also with skip connections to the decoder to pass on fine-grained information. So the decoder basically is just the inverse set of the encoder, where it consists of 2D deconvolutional layers. And in terms of the discriminator, it features a similar setting as the encoder of the generator, where it consists of 5 layers of 2D convolutional layers with another fully connected layers to output the probability. So the loss functions we use include the wet system loss, as it has been reported to help improve the stability and robustness of a GAN model. We also include the relativistic loss and the relativistic average loss, because both of them have reported to actually bring additional information to the GAN model and help the system's performance. So we further include another metric loss functions, where basically the discriminator trying to simulate a metric, an objective matrix. It could be a task, a story, or any other metrics. So the discriminator learns the distribution of the actual metric score, and a generator should generate the enhanced speech spectrograms with higher metric scores. So that's the intuition of this loss function. So in terms of the experimental setup, the data set we used are presented in the PIRA studies, where there are in total 28 speakers. Half of them are male speakers used in the training set, and there's another 2 different speakers used in the test set. So in the training set, there are more than 11,000 speech utterances that is mixed with 10 different noises at 4 different SNRs, 0, 5, 10, and 15 dB SNR. So in terms of the testing set, there are 824 utterances mixed with 5 different noises at 2.5, 7.5, 12.5, and 17.5 dB SNRs. And all signals have a sampling rate of 16 kilohertz. And in terms of the audio feature, we used a 512-point FFT for the short time Fourier transform with a 25 milliseconds window size and 10 milliseconds hop size. So in terms of the network setting, for the wet system CR GAN and the relativistic average CR GAN, the training target is the phase-sensitive mask. And the number of feature maps in the respective convolutional layers of the generator's encoder are 16, 32, 64, 128, and 256. The generator's decoder follows a reverse parameter setting of the encoder, and the bidirectional LSTM consists of 2,048 units per layer. The kernel size is 1/3 for the first convolutional layer and 2/3 for the remaining layers, with a stride size of 1/2. So for the discriminator, the number of feature maps are 4, 8, 16, 32, and 64 for the respective convolutional layers. All models are trained with 60 epochs with add-in optimizer. And in terms of the system we evaluated, first we evaluated our proposed CR GANs with the different loss functions that are described earlier. We also include some other previous GAN-based approaches, such as the CGAN, MMSE GAN, RS GAN, RAS GAN, and metric GAN. We also include a fully convolutional network, a convolutional recurrent network, an LSTM-based network, and another bidirectional LSTM-based network as the non-GAN-based approaches. And all the models, CR GAN models without the recurrent layers, we investigate them to investigate the influence of the recurrent structures. So here are the simulation results. So we found that our best approach, which is the metric GAN with the additional mean square error term, achieves much better performance in speech quality than all these PIRA GAN-based models in the first block. So we also noticed that our CR GAN-based approaches outperform other non-GAN-based systems across nearly all metrics. So these are the non-GAN-based systems, including the convolutional neural network with the mean square error as the loss function, LSTM network, bidirectional LSTM network, and the convolutional recurrent network. So basically, we found our system, the proposed CR-GAN systems, outperform this non-GAN based systems across this matrix by a large margin. And also we noticed that there's like a superior performance achieved by our CR-GAN models compared to the convolutional, convolutional recurrent network alone. So this one is trained with the mean square error turn, error loss, and without the adversarial training scheme. So basically it suggests that introducing the adversarial training scheme is helpful because it can improve the objective scores. And also we noticed that when the recurrent layers are removed by comparing these two blocks, so this block is our proposed CR-GAN models, and this block is basically showing you these models without the recurrent layers. So we noticed there's a dramatic decrease in terms of the PASC score, STOI, C6, CBAC-C overall. So basically, it suggests that the recurrent layers are important for our CR-GAN models, and it actually can improve the system's performance. So in conclusions, we proposed a novel GAN-based speech enhancement algorithm with convolutional recurrent structure that operates in the time frequency domain. The results show that our proposed models outperform other state-of-the-art GAN-based and non-GAN-based speech enhancement systems across an array of evaluation metrics, and it is promising to use the GAN framework for speech enhancement. Also, the introduction of recurrent layers is important for our CR-GAN model, and the metric loss among all the loss functions we investigated can greatly improve the performance. And by combining the metric and MSE loss functions, the CR-GAN approach can achieve even greater performance. And here are the references for this presentation. And finally, I would like to thank everyone for your time and attention, and that's all.